The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So hopefully you got practice with cross products and computing them in recitation yesterday. Let me just point out one important application of cross product that maybe you haven't seen yet. So let's say that I'm given 3 points in space, and I want to find the equation of a plane that contains them. So say I have P1, P2, P3, 3 points in space. Well, they determine a plane, I mean, at least if they are not aligned. And we would like to find the equation of the plane that they determine. So that means, let's say that we have a point P in space with coordinates x, y, z. Well, the equation of the plane let's say the plane containing P1, P2, and P3. So that means find a condition. We need to find a condition on the coordinates x, y, z telling us whether P is in the plane or not. Okay, so we have several ways of doing that. For example, one thing we could do, let me just backtrack to determinants that we saw last time. So one way to think about it is to consider these vectors P1, P2, P1, P3, and P1, P. Okay? So the question of whether they're all in the same plane is the same as asking ourselves whether the parallelepiped that they form is actually completely flattened. Right? If I try to form a parallelepiped with these 3 sides, well, if P is not in the plane, then it will have some volume. But if P is in the plane, that means that it's actually completely squished. So one possible answer, one way to think of the equation of a plane should be that the determinant of these vectors should be 0. Determinant of P1, P2, P1, P3, and actually let me do it in a different order. It doesn't really matter, but so one possible way to express the condition that P is in the plane is to say that the determinant of these 3 vectors has to be 0. And if I'm given coordinates for these points, I mean, I'm not giving you numbers, but if I gave you numbers, then you would be able to plug these numbers in. So you could compute these 2 vectors explicitly. You would have numbers here. But here, of course, this would depend on x, y, and z. So when you compute the determinant, you get a formula that involves x, y, and z, and you will find that this condition on x, y, z, that's the equation of a plane. Okay, so we're going to see more about that pretty soon. Now let me tell you about a slightly faster way of doing it. Actually, it's not much faster. It's pretty much the same calculation, but it's maybe more enlightening. Oh, let me actually show you the nice color picture that I prepared for this. Okay, so, right. So one thing that's on this picture that I haven't drawn there is the normal vector to the plane. So why is that? Well, let's say that we know how to find a vector that's perpendicular to our plane. Then what does it mean for the point P to be in the plane? Well, it means that the direction, say, from P1 to P has to be perpendicular to this vector n. Okay? So here's another solution. So P is in the plane only when, well, exactly when the vector P1P is perpendicular to n, where n is some vector that's perpendicular to the plane. So that's called a normal vector. Not that the others are abnormal, but okay. So how do we rephrase this condition? Well, we've learned how to detect whether two vectors are perpendicular to each other using dot product. Okay, dot product. That's the first lecture. So these two vectors are perpendicular exactly when their dot product is 0. Okay, and so now concretely, well, if we have a point P1 given to us and say we have been able to compute the vector n, then, well, when we actually compute what happens, here we will have the coordinates x, y, z of a point P, and we'll get some condition on x, y, z. That will be the equation of a plane again. Okay. Now, why are these things the same? Well, before I can tell you that, I should tell you how can we find a normal vector. But maybe you are already starting to see what the method should be, because we know how to find vectors perpendicular to two given vectors. Right? So we know two vectors in that plane, for example, P1, P2, and P1, P3. Actually, I could have used, another permutation of the points, but let's use these. So if I want to find a vector that's perpendicular to both P1, P2, and P1, P3 at the same time, all I have to do is take their cross product. So how do we find this vector that's perpendicular to the plane? Well, the answer is we can just take the cross product P1, P2 cross P1, P3. I should say, well, say that actually you took the points in a different order. You did P1, P3 cross P1, P2. You would get, of course, the opposite vector. That is fine. Any plane has actually infinitely many normal vectors. You can just multiply the normal vector by any constant. You will still get a normal vector. That's absolutely fine. So that's going to be one of the main uses of dot product, C. When we know two vectors in a plane, it lets us find the normal vector to the plane, and that is what we need to find the equation. Now, why is that the same as the answer over there? Well, the condition that we have is that P1P dot n should be 0. And we said n is actually P1, P2 cross P1, P3. So this is what we want to be 0. Now, if you remember stuff from a long time ago, that was Friday, then we've introduced this thing and called it the triple product. Okay, and what we've seen is that the triple product is the same thing as the determinant. So in fact, these two ways of thinking, one saying that the box formed by these three vectors should be flat and have volume 0, and the other one saying that we can find a normal vector and then express the condition that a vector is in the plane if it's perpendicular to the normal vector, they're actually giving us the same formula in the end. Okay. Any quick questions before we move on? Yes? So these two quantities, P1P dot cross product, or the determinant of the three vectors, they're always equal to each other. Okay, they're always the same. And now if a point is not in the plane, then the numerical value will be non-zero. If P is in the plane, it will be 0.